Okay, my friends, here we are with a quick video to talk about derivatives of exponential and logarithmic functions. Because this is my second time recording this, because the first time I didn't record, I'm going to take just 1 second to make sure I actually am recording. I am. And now you're going to probably get the streamlined version, hopefully, because I've already done this once. Okay, so at this point, you should know how to do all the things: power rule, product rule, quotient rule, chain rule, derivatives of trig functions, derivatives of inverse trig functions. The only thing we haven't done is derivatives of exponential and log functions. So you are going to learn 4 new rules today. We'll explain why it's 4 in a second. And then that will be kind of your final list of things you are expected to be able to take the derivative of. If we were in live school, you would have done some exploration of this, combining the things we did with in class on Monday. So you would have practiced using your calculator to graph the derivative of each function, and then you would draw a sketch of what the derivative looks like and kind of explain why that makes sense using slope. And then you would use the table feature to try to figure out what the derivative function actually is. So you might be able to tell from just the graph, but the table would really help. So if you're in an exploratory mood, there are 1, 2, 3, 4 examples to explore. And basically what you could do is go into y1 of your calculator and graph the function, and then go into y2 and use math 8, like we talked about in class on Monday, to graph the derivative and see if you can figure out the rule. And then you could repeat the same thing here. Put this in y1, go into y2 and graph the derivative using math 8 on your calculator and see if you can figure out the rule. And then this in general box was for you to try to sum up the rule and then do the same thing here. So here were 2 examples with exponential functions, and here were 2 examples with log functions. Because it's not super easy for me to try to graph live on my calculator and do all that, we're going to skip. So on the next slide, I'm going to just tell you the 4 derivative rules. But I am going to visit these back once you know the rules to kind of show you some cool things about them. So if you want, pause and do that activity. If not, next slide. Here are your 4 derivative rules. And there are 2 of them for exponential functions and 2 of them for logarithmic functions, because the rules vary a little bit whether you have e to some power or just like 5 to some power. And then same thing for logs. You have 1 rule specially for natural log, and then you have another rule for all other logs. So like log base 2, log base 5, log base 10, and so on. So take a second to pause and copy these down. I'm going to point out some things that I think will be helpful so that these don't seem super overwhelming. First things first, notice all of them have du dx, and that is them just building in chain rule into the problem so that you don't forget that almost all exponential and log functions will have chain rule, and this du dx comes from multiplying by the derivative of the inside function, and the inside function for an exponential is going to be whatever the exponent function is. So if you have like e to the 5x, 5x would be your inside, so here you would be multiplying by the derivative of that. And then for log functions, it's exactly what you think it is. The inside is the argument. So if you have natural log of 7x squared plus 6x, well, you're going to have to multiply by the derivative of the inside to account for chain rule. So this is just reminding you that almost all exponential and log functions will use chain rule, unless you're just doing like e to the x or natural log of x, because the chain rule would just have you multiply by 1 on the derivative of the inside of each of these. So we're going to just do 1 quick example of each of these here, and then the next slides have a whole bunch of examples. So just so that you get the rule, basically with an exponential, so say we're going to just start with an easy one. Say I was taking the derivative of e to the 6x. Well, the derivative says keep it the same. The derivative is going to be an exponential too. It's going to be e to the 6x. But then times the derivative of the inside times 6. So the derivative of e to the 6x is actually 6e to the 6x. And we're going to talk in a second about why it makes sense that the derivative of an exponential is an exponential. Okay, so there's a little bit of a difference if the base isn't e. So say we're trying to take the derivative of 7 to the 6x. Well, the derivative of 7 to the 6x says keep it all the same, so 7 to the 6x again, times natural log of the base. And a represents the base, which is 7, so times natural log of 7. Remember, natural log of 7 is just a constant. So there's this interesting idea that when we do a to the u, we're actually multiplying by another constant. And then we're also going to multiply by the derivative of the inside, which would be the derivative of the exponent, which is 6. So the derivative of 7 to the 6x is 7 to the 6x times natural log of 7 times 6. I want you to notice that these rules are actually the same. So e to the u times du dx times natural log of a, which in this case, the base is e. And natural log of e is just 1. So that's why we write it as kind of two separate rules, but it really is the same thing. So the rule in general is keep it the same, multiply by the derivative of the inside, and then if it's not base e, you also have to multiply by natural log of whatever the base is. So that gets you exponential functions, and big takeaway here that we're going to revisit in a second is that the derivative of an exponential is an exponential. Pretty cool. Okay, now let's take a look and do a little breakdown of the log rules. So for natural log, the derivative, so say we're taking the derivative of natural log of 3x plus 8. The derivative of natural log of 3x plus 8 is 1 over u, where u is the argument, so 1 over 3x plus 8, times the derivative of the inside. So the derivative of the inside was 3. So we would really write it as 3 over 3x plus 8. Okay, and then again we have that slight difference if the log is not natural log, if it's some other base. So say I'm going to take the derivative of log base 6 of 3x plus 8. Well, the derivative of that is going to be 1 over u, so 1 over the argument, 3x plus 8, times, there's some other constant in the bottom, natural log of a, so times natural log of 6, because 6 is the base, and then times the derivative of the inside, so times 3. So final answer, sorry, my dog is digging if you can hear something scratching. So 3 over 3x plus 8 times natural log of 6. So here's the function, and here's its derivative. Okay? And thing I want you to note here, again, it's really just the same rule, but natural log of e is 1. So we have this little added piece we have to remember, a little constant that gets added when it's not a natural log function we're taking the derivative of. And big takeaway here is that the derivative of any type of log function, log or natural log, is going to be a rational function. It's going to be a fraction. Okay. My dog is really digging. He was so great during the first video. Come on, bud, sit down. He's getting impatient with me. So I just want to make just a couple quick connections to here. So if you were to do this activity, based on what we just did, the original function here was e to the x, and the derivative of it would be e to the x times the derivative of the inside, which is 1. So I want you to realize what that means. It means the derivative of e to the x is e to the x. Well, let's think about that based on slope. So if this is my original function graphed in red, that's e to the x. What do you notice about the slope originally? Well, the slope originally is close to 0. It's almost flat. So the slope originally is close to 0. And then what's happening to the slope? It's increasing in the positive direction and getting steeper and steeper and steeper. So the derivative is increasing in the positive direction and getting steeper and steeper and steeper. So it makes sense that the derivative of an exponential is also an exponential. Here, the only difference when we have f prime of x is equal to e to the 2x, Well, based on our derivative rules, the derivative, f of x is equal to e to the 2x. The derivative would be e to the 2x times the derivative of the inside times 2. So here, our derivative is not going to be exactly the same. It's going to be 2 times e to the 2x, which still means if you look, the slope starts at 0, this graph's almost flat, and then the graph gets faster and faster, increasing and increasing and increasing, right? The only difference here is that the derivative actually increases at 2 times the speed. The slope is changing twice as fast as the function is changing. But it hopefully makes sense to you that the derivative of an exponential is an exponential. I want to really quickly just look at one of the log ones. So in this function, it was f of x equals natural log of x minus 2. And practicing, I know the rules we just learned, but the derivative of a log function is 1 over the argument times the derivative of the inside, which would just be 1. So notice this is a rational function that has a vertical asymptote at 2. Well, why would the derivative have a vertical asymptote at 2? Well, because the slope is so steep it's vertical there. So if the slope's vertical, it means, or if the tangent line's vertical, it means the derivative's undefined. So our derivative is going to be undefined at 2 because that's where our slope is a vertical line. And then, so our derivative is super steep. It's like positive infinity, right? It's so steep here. And then notice the derivative stays positive but gets less and less steep until it approaches 0, right? Because this graph is flattening out. So when I go to draw the derivative, I'm going to have that vertical asymptote. And then my graph is going to get less steep and less steep and less steep until it approaches 0. So what we've created here is the rational function 1 over x minus 2. And notice that as the slope gets closer and closer to 0, the derivative is getting closer and closer to 0 using that rational function. Okay, so hopefully, again, you can keep exploring this on your own if you would like, but we're going to just jump into some examples. So here are 5 examples of derivatives of exponential functions, and then we have 4 examples of derivatives of log functions. You do not need to listen to me walk through these if that's not what's most helpful to you. You can just pause the video, do the problems, and then just fast forward until you see the answers and just make sure we agree. If not, I'm going to go through each of the problems. So first, I'm just going to rewrite here our rules. The derivative of e to the u is keep it the same times the derivative of the inside, where the inside is the exponent. Our other option is if it's not base e, so let's say it's 7 to the u, we're going to call that a. The derivative is keep it the same times natural log of a times the derivative of the inside. So now we're going to apply those rules to these problems. So the first one, remember this is not, now another dog's barking, so my dog's barking. What a disaster today. So this is not product rule because 2 is just a constant. So we're going to keep 2. And then we're going to multiply by the derivative of the inside. Oh my God. Then we're going to multiply by the derivative of e to the x. So I'm going to keep 2. And the derivative of e to the x is keep it the same times the derivative of the inside, which is just 1. So y prime is going to be 2e to the x. For our next one, this is an exponential. The derivative is keep it the same times the derivative of the inside, which would be -1. You're not going to write it like that. Instead, you would write negative e to the negative x. So the derivative of e to the negative x is negative e to the negative x, which came from keep it the same times the derivative of the inside. Next one. At first, I thought that was product rule, and then realized e squared is just a number, right? It's like having, right, e squared is like about 5, because e is about 2.7. So this is really like just saying 5x. Well, what's the derivative of 5x? Just 5. So the derivative of e squared x is just e squared. Minus the derivative of e to the x is keep it the same times the derivative of the inside, which is 1. So it would be e squared minus e to the x. Here on the right side, now we have some with the base not e. So y prime, this is a to the u. So keep it the same times natural log of the base, which is 8, times the derivative of the inside, which is 5. So it looks a little gross, but that is the derivative of that exponential. And natural log of 8 and 5 are just constants. So really we just have some constant being multiplied by 8 to the 5x minus 6. And then last one, the derivative, keep it the same. So 3 cosecant of 2x times natural log of the base, which is 3, times derivative of the inside. So what is the derivative of this exponent? This is a little bit of a throwback. The derivative of cosecant is negative cosecant cotangent. And then times, chain rule again, the derivative of the inside, which is 2. So this would be a to the u times natural log of a times the derivative of u, and u would be this exponent, and the derivative of cosecant is negative cosecant u cotangent u, sorry there's an x here, times 2. Okay, now let's take a look at the natural log and the log ones. So the derivative of natural log of u is 1 over u times du dx, chain rule. If we're not looking at natural log and we're doing some other base, let's call it a. So a to the u, the derivative of that is 1 over u times natural log of a in the denominator, and then times the derivative of the inside. So 2 to practice with natural log, 2 to practice with some other base. So y prime is going to be 1 over the argument times the derivative of the argument. We can write it a little better like we did with our inverse trig and just say 2x plus 6 over x squared plus 6x. Next one, y prime, 1 over the argument, x minus 4 over x squared, times the derivative of the argument, 1, this remember is the same as 4x to the negative 2, so it'll be plus 8x to the negative 3. So 1 plus 8x to the negative 3 over x minus 4 over x squared. My dog is out of control right now. Sorry, he really doesn't do well with like packages and deliveries. And obviously the mail person's walking around. Okay, next one. Y prime is 1 over u, 3x minus 6. Also, because it's not natural log, times natural log of 4, times the derivative of the inside, which is 3. So we could write it like this. Cool. And then final one, not product rule. Natural log of 2 is just a constant. I threw that in there, obviously, because I was trying to trick people up and make sure they were paying attention. So natural log of 2 is just a constant. So now take the derivative of log base 2 of x. So 1 over u, which is x, times natural log of 2, times the derivative of the inside is just 1. So this one actually can simplify a bunch, and basically the derivative of that is just 1 over x. So hope that was helpful. It really just takes practice. So do your problem set, practice, and you will have those 4 rules down pat. And let me know if you need anything. See you Thursday.